This is a modified version of lecture 28 where we focus specifically on subspaces of Rn. If you want to look at subspaces of vector spaces in general, you should look at the original lectures 27 and 28. So we say that Rn is a vector space because it has these 10 properties. And we've seen these properties before. We've talked about, for example, commutativity. So number 2 here is the commutativity of the vector addition operations. That's the commutative property. Not all of these have specific names. You're not responsible necessarily for knowing what these names are, but these are the 10 properties that create what we call a vector space. So when we have a subset of Rn, we say that that subset is a subspace if it also has those same 10 properties. But it turns out that some of those properties are what we call inherited from Rn automatically. So if we put these two things side by side, so if we say that U is a subspace of Rn, again, that means it's a subset and it has the same 10 properties. So we see these 10 properties side by side. What we're going to notice is that some of these properties are just inherent to the operation that's happening in Rn. So let's talk about commutativity again. So if we know that U plus V equals V plus U in all of Rn, then certainly in this subset, it's still going to be true that U plus V equals V plus U. If we throw away some of the vectors in Rn and look at this smaller subset of Rn, then we're not going to lose the fact that the addition operation is commutative. That's going to be preserved. So what we see here is that the operation, or the axioms here that I've colored in blue, those are what we call inherited operations, or inherited axioms. So those are axioms that we don't have to check again for this subset. But the ones that specifically refer to U rather than referring to properties of the actual operations, those are the ones that we would actually have to check. So if we have inside of our, however many n-dimensional space, we've got this subset, we need to check, for example, is it actually true that when you take two elements of this subset and add them together, you get another element of that subset? Does this set have a zero vector in it? And so on. So these are the four things that we would have to check to see if the subset is actually a subspace. So here's the definition. So a subspace U of Rn is a subset such that the zero vector is in there. U is closed under vector addition. So that's how we describe this fact that if U and V are vectors in U, then U plus V is still in U. And then U is closed under scalar multiplication. Again, if little u is a vector in capital U and C is a scalar, then C times U is in capital U. Now, if you look back at that previous slide, you might notice that I left out something. I left out the axiom about additive inverses. So why don't we need that? Well, if we know that U is closed under vector addition, and we know that U is closed under scalar multiplication, then what we're going to know is that -1 times any vector U. So if little u is in capital U, then -1 times U, that's also going to be in capital U. And this, using the vector addition and other closure operations, other properties of our operations, this is going to be in the additive inverse of little u. Because if I take little u plus -1 times little u, well, 1, that's going to be multiplying 1 by u, that's not going to do anything. And then I can use distributivity, I can basically factor 1 plus -1 times u, that's going to be 0 times u, that's going to be the zero vector. So we don't need to specifically check that additive inverses are in there. Okay, so let's do some examples. So this all seems sort of abstract, so let me try to make it seem a little bit more down to earth for you. So we're going to do several examples here. Some of these are going to be subspaces, some of these are not going to be subspaces, and we're just going to practice going through this checklist. So the first thing we need to check is this set a subset of R2? Well, first let's try to understand this notation. I know this notation throws people off sometimes. So what does this mean? So this means vectors of the form A to A, where A is in R, where A is a real number. So we're talking about vectors like 5, 10. We're talking about vectors like -6, -12. We're talking about vectors like 3, 6, and so on. Pi, 2 pi. So those are the kinds of vectors that we're talking about. So we take all of those vectors, we throw that in a set. That's a subset of R2, right? Because those are all vectors that are in R2. So all vectors A to A are in R2. because it's pretty easy to get into R2. All you have to do is have 2 entries, and all of these vectors have 2 entries. So the second, third, and fourth things here, those are the ones that are going to require a little bit more work. So is the 0 vector in my set capital U? So does the 0 vector look like the form A2A for some real number A? Well, hopefully you see that yes, it does, because I can write A equaling 0, and 0 and then 2 times 0 as my 2 entries. That's going to be in my set U. So I should say here is actually an element of capital U. So that's a check. Now, the first 2 of these, as we're going to see as we go through these examples, those are usually the easier ones to do. And then the third and fourth ones, those are the closure ones. Those are going to be the ones that are going to be a little bit more work. Okay, so let's look at why is the set U closed under vector addition. So we've got an if-then statement. So there's our hypothesis. There's our conclusion. So we're going to start with the hypothesis. We're going to say let U1 and U2 be elements of capital U. All right, and then our conclusion is going to be, therefore, U1 plus U2 is in capital U. So let U1 and U2 be in capital U. What do we now know about U1 and U2? Well, all we know is the definition of capital U. All we know is the way capital U is defined, which is this thing up here. So we know that U1 has the form A2A, and we know that U2 has that same form. Now, we don't want to use the letter A again because we don't know that these 2 vectors are the same vector. They might be different vectors. So maybe I'll call it B2B. Right, all I'm really trying to say is that these vectors have the form where the first entry, the second entry is double the first entry. And so we're just doing that algebraically by using letters here. So U1 is A2A and U2 is B2B for some real numbers A and B. Okay, so that's what I get out of my hypothesis. Now I'm going to start working towards my conclusion. My conclusion says U1 plus U2 is in capital U. Okay, so I'm going to take these 2 vectors and add them together. So now U1 plus U2, well, that's going to be A2A plus B2B, and that's going to be A plus B, and then if I do a little bit of algebra, 2 times A plus B. And that's in capital U because what capital U is vectors where the second entry is double the first entry, and that's what this is. So that checks our closure under vector addition. And then closure under scalar multiplication is going to look pretty similar. Again, we're going to start with our hypothesis, which is this stuff here. We're going to end with our conclusion. So we're going to say let little u be a vector in capital U, and let c be a real number. What does it mean for little u to be in capital U? What it means is that u has the form A2A for some real number A. Now we're going to work towards our conclusion. Our conclusion talks about c times u. Okay, so what's c times u? Well, that's going to be c times A, and then again a little bit of algebra, 2 times c times A. And that's in U because what does it mean to be in U? It means that the second entry is double the first entry, right? We keep going back to that definition of U in this problem. And so that shows that we're closed under scalar multiplication. So it's a proof, but it's hopefully not too bad. Again, it's a simple if-then statement. Start with the hypothesis, use the definition of your subset, and then work towards your conclusion. All right, let's do another example. So this time our set U is just a very simple set. It's only got the 0 vector in it. So it's got a single vector that happens to just be the 0 vector. And we want to prove that U is a subspace of Rn. So again, we're going to go through our checklist. Is this a subset of Rn? Again, the only thing we have to make sure of there is that all of the vectors in our set are vectors that are in Rn. And certainly this 0 vector is in Rn. So yes, right? We had to make sure that all of the vectors in our set are in Rn. We've only got one vector in our set. It's in Rn, so we're good. And then also takes care of the second bullet on our checklist. Is the 0 vector in U? Well, the 0 vector is the only thing in U. So yes, the 0 vector is in U by the definition. All right, what about our closure properties? So again, we're going to start the way we did previously. So we're going to say let U1 and u2 be vectors in capital U. And again, our conclusion, what we're trying to do is prove that u1 plus u2 is in capital U. Now, again, the second step here, sorry about that, had an airplane going over my house. The second step here would be to use the definition of capital U and say, okay, now what do we know about these two vectors from the fact that they're in capital U? Well, the only vector in capital U is the 0 vector. So that means that little u1 has to be the 0 vector because that's the only vector in capital U. And little u2, that's the 0 vector because that's the only vector in capital U. So now the conclusion would say u1 plus u2, what's that? Well, that's 0 plus 0. 0 plus 0 is 0, and that's in capital U because it's the only thing in capital U. And that's what we wanted, so we're done with that one. Similarly, for scalar multiplication, I'm going to say let little u, vector little u, be in capital U, and let c be a real number. And again, because of the definition of capital U, this vector little u has to be the 0 vector because the 0 vector is the only vector in this set for this example. So now what's c times u? Well, that's c times the 0 vector. Anything times the 0 vector is the 0 vector, and that's in capital U because the 0 vector is the only thing in capital U. So that's a check as well, and we're done with our checklist. So this is a little bit of a strange example because our set only had one single vector in it, but when that single vector is the 0 vector, this again turns out to be a subspace. Now let's look at some non-examples. So the vector space R2 is not a subspace of R3. So even though we can sometimes think of the xy plane as kind of living inside of three-dimensional space, that's really just a copy of R2. So R2, these are vectors of the form AB, and the vectors R3, those are vectors of the form ABC. So R2 is not a subspace of R3 because it's not a subset of R3. These vectors have 2 entries, but these vectors have 3 entries, and so R2 does not actually live inside of R3. It's just simply a copy of R2 that lives inside of R3. And this set here, this is a subspace of R3. And again, we could go through and check. This would be very similar to example 1 that we did. Another non-example, a line that doesn't pass through the origin is not a subspace of R2. And there's a lot of reasons why. This time, this is a subset, right? All of the vectors that live in this line, right? So this would be an example of a vector that's in this set. All of those vectors are in R2, so it is a subset. But for example, it doesn't contain 0. So it doesn't contain the 0 vector because it doesn't pass through the origin. So that's already one strike against it, and that's enough. We could stop right there, and that would be enough for us to see that it's not a subspace. But there's more that's wrong. If I picked another vector, so let's say this vector here, here we have 2 vectors that are in my subset, but if I add them together, draw my little parallelogram, I get a new vector, and this vector is not in my subset U, and so it's not closed under vector addition. It's also not closed under scalar multiplication. That's what I was about to write, but I'll get that next. Vector addition. So that's another strike against it. Again, we only need 1 strike for this to not work, but this one we have a lot of strikes. And if I now multiply one of these vectors by a scalar, let's say I take this vector, the first vector I drew, and multiply it by 2. So this would be, so let's say I call this an original vector u. This new vector that I got by multiplying by 2, maybe I'll call that 2u. So 2u is not in capital U, because again, I can see that this green dot that I've drawn is not on my line. So again, a third strike against this is that it's not closed under scalar multiplication. So many ways to see why this is not a subspace. So another example of a subset that is a subspace is the span of a set of vectors. Okay, so let's remember what that means. The span of v1, v2 through vp here. So if I write this here, what does that mean? This means all linear combinations of v1, v2, etc. up through vp. So that's what that means. Remember, we're using span as a noun here, right? So it's the span of those vectors. That's just all the linear combinations. So we want to show that that is a subspace of Rn. So is it a subset of Rn? So in other words, is a linear combination of those vectors, if the vectors are coming from Rn, right, we know that from this, is that linear combination also in Rn? So if v1, v2, up through vp are in Rn, is c1 v1 plus c2 v2 plus cp vp, is that in Rn? And of course the answer is yes, because how would you get out of Rn? The only way that you could not be in Rn is if somehow the number of entries in your vector changed. And if we multiply a vector by a scalar, that doesn't change the number of entries. And if we add two vectors that have the same number of entries, the result still has the same number of entries. So all of these vectors have n entries. So again, the only thing that can go wrong for this first thing that we check, for the subset, is if we have the wrong number of entries. It's the only thing that can break here. So continuing with our proof here, the next thing we have to check is the zero vector in capital U? So in other words, is the zero vector one of the linear combinations in the span? Because that's what U is. So U, capital U, is the set of all of the linear combinations of the V vectors. And so the question is the zero vector one of those? Well, again, all we have to do is construct a linear combination that gives us the zero vector. And we can do that simply by using 0, the scalar 0, as the weight for every vector. And that is in the span of those vectors, because that is one of the linear combinations that we can construct. Now, maybe these vectors are linearly dependent, and maybe there's a different way to construct the zero vector. We don't care about that. All we care about is whether or not there is some way to construct the zero vector. So now we get to sort of more the meat of what we have to do. As usual, this third and fourth things on our checklist, those are the ones that require a little bit more work. So if U1 and U2, if those are vectors in capital U, is the sum of those two vectors in capital U. So we're always going to start this the same way. We're always going to start by saying let U1 vector and U2 vector be in capital U. So doesn't give us much, but at least gets us started. The second thing we're going to do when we do this part of our proof is we're going to use the definition of capital U to figure out what that means. Okay, so capital U, that's this. That's my capital U, is the span of those vectors. Okay. So what do I know about U1 and U2 from knowing that they are in the span? Well, what is the span? The span is the set of all the linear combinations. So that means that U1 vector and U2 vector are two of the many linear combinations in the span. So that means that U1 looks like C1 V1 plus C2 V2 plus CP VP for some scalars C1 through CP. And U2 also looks like that, but probably not using C's again, right? Because it's probably not the exact same linear combination. So I should probably use different letters for my linear combination. Maybe I'll call them D. So D1 V1 plus D2 V2 plus DP VP for some scalars D1 through DP. Okay, so that's what I get out of knowing that U1 and U2 are in capital U. Okay, so what do I do now? Well, now I work towards the conclusion. So again, this is going to be the next step. First step is to say let U1 and U2 be in capital U. Second step is to use the definition of capital U to figure out what that tells you. Next step is to start working towards your conclusion. And in this case, we're going to add these two vectors together. So what's U1 plus U2? Well, I can add these together in different ways, but I've specifically lined these up because I want to group together the V1s and I want to group together the V2s and so on. So I'm going to get C1 V1 plus D1 V1, and then I'm going to get C2 V2 plus D2 V2, and then the next thing that I would write would be C3 V3 plus D3 V3, and so on, but I'm just going to put dot, dot, dot. And then finally CP VP plus DP VP. And now I'm going to factor a little bit. I'm going to take out the C1 plus the D1 multiplied by V1, C2 plus the D2 multiplied by V2, and so on. And then finally CP plus the VP, plus DP multiplied by VP. Clean that up a little bit, make that easier to read. There we go. So that is a linear combination of the V1, V2, and so on, right? Because it's a scalar multiplied by V1, scalar multiplied by V2, scalar multiplied by VP. That's what it means to be a linear combination. It means you've got a scalar multiplied by each vector, and then you add the results together. So that is in the span of V1, V2, up through VP. Check. Okay, so it's a little bit alphabet soupy here, but hopefully that made some sense. Last up, again, similar kind of thing, closed under scalar multiplication. How do we work through this? Again, step by step, it's going to be very similar. As you work through these examples, you're going to see some similarities. First step is to say let little u be in capital U, and let little c be in the real numbers. Little c be a scalar. So always going to say that. You're always going to start there. Okay. Second thing you're going to do is going to be to use the definition of capital U to figure out what the heck does this tell me? What do I know now from knowing that little u is in capital U? Well, in this case, because my capital U is my span, I know that little u is a linear combination of the v's. So kind of similar to what we did before, except this time we only have the one vector. Little u is that linear combination. This second step is going to be different depending on what your actual set capital U is. In this case, because my set capital U is a big set of linear combinations, I know that my vector little u is a linear combination. If my set capital U is defined in a different way, this step is going to look a little bit different. But in this case, I know that this is true for some scalars C1 through CP. Okay, so now third step is to work towards the conclusion. My conclusion here is that C times U should be in capital U. Okay, so what's C times U? C times U, that's C times all this stuff, C1 V1 plus C2 V2 plus CP VP. And now I'm going to distribute. So I've got C, C1, V1. I've got C, C2, V2. And then I've got C, CP, VP. But if I draw parentheses here, and again, using my vector space axioms, I can do this. Draw parentheses there and there and there. What I see is that, again, this is a linear combination of the v's because it looks like scalar times v1 plus scalar times v2 plus scalar times vp. That is in the span of v1, v2, up through vp. And again, that's a check because that's what I was going for. So that's it for this proof, for this theorem. Again, most of the proofs that you're going to do are going to be the same kind of structure, maybe a little bit less abstract, but follow this outline, right? So you've got an if-then statement, start with a hypothesis, use the definition of your subset, and then try to work towards your conclusion.